serving as the project manager for the Stream Stewardship team. We're the largest team of any of the teams, with 12 students, and perhaps also the most energetic. Luckily, the students were able to put this manpower and enthusiasm to use, conducting hands-on repair and restoration. The best part of which I thought was learning how to use gas-powered weed whackers. I spent most of my job making sure that all the liability waivers were signed. In all seriousness, though, this is my first time ever managing a team this size, and I couldn't have imagined a happier, more gung-ho, hardworking, and diverse group of students, and it's been a real pleasure getting to work with all of you.
Hi everyone, so thanks so much for being here. We are representing the Stream Stewardship team of 2012, and we are the ELP's 8th team to focus on stream restoration. This year our partners were the Mackenzie Watershed Council and the Mackenzie River Trust, two organizations dedicated to protecting the abundant resources in the Mackenzie watershed. So here's a brief overview of what we'll be talking about. I'll start with the introduction of the Mackenzie River watershed, and then talk about the historic and current threats to the Mackenzie River and the need for restoration projects. Then we'll have Ben, Sean, and Thomas talk about our 3 projects. This is the Mackenzie watershed. As we learned from my Mackenzie, the Mackenzie River is 90 miles long. Its headwaters are up in the Cascades, and it flows down until it meets the Mackenzie River just north of Eugene. The 3 stars indicate our project sites. The Mackenzie River is important for many reasons. The lower reaches contain some of the few remaining braided side channels. Braided side channels occur when a stream is traveling at a high speed and carrying a lot of sediment. Sediment is deposited as island bars, creating a braided pattern in the water. Second, the Mackenzie is home to the pictured spring chinook, salmon, and Oregon chub, which are both listed as endangered species, threatened under the Endangered Species Act. And lastly, the Mackenzie is a sole source of drinking water for more than 200,000 people. While the Mackenzie is rich with resources, it has suffered greatly from human impact. There are 6 dams on the river, and much of the surrounding land is used for agriculture. And in addition, humans have introduced many invasive species such as reed canary grass. Our goals for all 3 of the projects were to enhance riparian zones. Riparian zones are the areas directly adjacent to streams and rivers, the intersection of aquatic and terrestrial life. Ideal conditions include native species diversity. Native species promote a healthy and balanced ecosystem. Dense vegetation cover and overstory seen there provides shade and in turn decreases water temperatures. And lastly, bank stability decreases erosion and sedimentation to streams as seen here. The Middle Mackenzie Side Channel, pictured in the bottom left, took place 55 miles east of Eugene at the Mackenzie River Campground. In October of 2011, the U.S. Forest Service fell trees into the river, a process known as large woody debris placement, in an effort to slow down water movement for spawning salmon. Last year's team conducted baseline monitoring so that future teams could determine the success of their efforts. The Berggren Watershed Conservation Area includes 50 acres of critical riparian habitat that we worked on. The land was acquired in a partnership between EWEB, the Mackenzie River Trust, and the Bonneville Power Administration in an effort to support the EWEB Drinking Water Source Protection Program. The land is managed by both the Mackenzie River Trust and the Mackenzie Watershed Council. And our 3rd site, the Old Mohawk Riparian Project, was located on the Mohawk River, the largest tributary of the Mackenzie River. It is privately owned and located 12 miles northeast of Springfield. And now I'll hand it over to Ben, who will tell you about our work with the Middle Mackenzie Side Channel.
Okay, so the Middle Mackenzie Side Channel project was a really fun project. We got to get out there and get in the river and really put to use some of the surveying techniques that we learned in the classroom over the past few months. And of these techniques, we conducted cross-channel surveys, gravel counts, and completed a longitudinal profile using surveyor's tools seen in this picture. And the sediment counts were used with the gravelometer right there. So the longitudinal profile was meant to compare the changes from 2011 to 2012 of the Thalwag, which is the deepest portion of the stream. Right here, you see the stream bed, and then the river, the water height right here. And the green dots indicate the large woody debris that was placed back in 2011, and the black triangles indicate the cross sections that we used affect our cross-channel surveys. And really what we were looking for was a change in stream complexity. You can see from 2011 to 2012, we had some scouring, which is the formation of little pools where the sediment was displaced, and then some deposition, which is the buildup of sediment a little further downstream. So for our gravel counts, we were looking at these two graphs right here, count 1 and count 2 on the bottom. Count 2 is taken from a little further upstream, count 1 downstream. And the red line indicates the 2012 data that we collected, and the blue line is the 2011 data collected by last year's team. We're looking at the D50 counts, which were the median sediment size within the stream in millimeters. And really what we wanted to see was a D50 count of about 35 millimeters, because that's the ideal sediment size for salmon spawning habitat. And in our graphs, you can see that there's a slight shift. This is a cumulative percentage going up the y-axis, and then a logarithmically increasing scale of millimeters on the x-axis. And you saw a slight shift to this portion of the graph in the curves, which indicates that some of the sediment size did decrease in count 1, which was, remember, further downstream. And we actually saw the opposite effect in the count 2, which was further upstream. And the sediment size, the D50 size, got a little bit larger in this year's count. And finally, we're looking at the embeddedness percentage within the stream bed, which is of the particles that we examined, the percentage of them that were embedded within the stream bed itself. We want to see a 25% embeddedness, because that's once again the ideal percentage for salmon spawning habitat. And we actually did see a decrease in both counts from 2011 to 2012. So for conclusions for the Middle Mackenzie Side Channel project, we did see an increase in stream complexity with the scouring further upstream and the displacement of the sediment and deposition towards the bottom of the stream of our longitudinal profile. And with that came the change in sediment distribution. We saw count 1, which was taken further downstream, had that increase in smaller particle size, which was probably due to the decrease in smaller particle size from upstream that came from the scouring and deposited lower down in the stream. As far as the overall effects of the large weight debris, they were implemented back in October 2011, so it's sort of difficult to tell if they've had a substantial effect on the stream yet. And if the results that we see correlate to the placement of large weight debris. But the fact is that both of these did change from last year's data, which could be indicative that the large weight debris is having an effect on the stream itself. Next, I'll hand it over to Sean to talk about the Bergen Watershed Conservation Area.
Yeah. We spent 5 weeks out of the Bergen Watershed Conservation Area performing restoration work out on the 90-acre plot. We specifically worked on 2.5 acres of land in the northwest region, but we also did surveys along the entire riparian strip. Our first phase of 3 phases for the restoration plan was to plant native shrubs and trees in 4 sample plots, as well as take photo points of each plot so that future projects can go in and use our data as well as see our photo points so they can make accurate evaluations of how it's going. After we planted our shrubs and trees, we matted and caged most of them with weed mats and various types of cages. The weed mats are meant to protect from the encroachment of invasive species, and the cages are meant to protect from browsers such as deer and beavers. After that, we implemented phase 2 of our restoration plan, which involved the manual removal of invasive species. Here, Thomas is seen joyfully pulling the Himalayan blackberries from the ground using his hands and a shovel to dig it out from the root. Some of us, as Keith said earlier, had a chance to use weed whackers. The weed whackers were meant to, Keith and Ben displaying them very joyously. We used the weed whackers to mow adjacent plots to our own for future sites to then go in and continue the restoration work. After they mowed these sites, we laid down insulation mats, joyfully, as you can see. which we stake them down with wooden posts and nails, and they'll be down for 2 years. These mats are meant to prevent the regeneration of the reed canary grass. And after 2 years, future projects will come in, remove the mats, and continue work planting native shrubs and trees in the area. During all that restoration work, some of us went out and performed invasive surveys. We went out in pairs along the riparian strip, all along this region at the BWCA, and we used GPS points to mark the exact locations of patches of these invasive species. The ones we focused on were herb roberts, evergreen clematis, Scotch broom, and English holly. Finally, phase 3 was we conducted baseline monitoring at our site. It's hard to see here, but our 4 plots had specific locations where we measured the baseline attributes of our plants and our shrubs and trees, primarily measuring things like their heights and their live crown heights. We accomplished a lot for Urban Site. We planted 250 native plants, and that's 20 species native to Oregon. We removed a lot of invasive species, and we got a chance to work with new equipment. And we also had a chance to work with Jared Wainwright throughout the entire thing, which was really awesome. And we finally got a chance to perform some baseline monitoring, which helped us with our other projects. Now, Thomas is going to talk about our final project at the Old Mohawk site.
So what we did at Berggren is essentially what last year's team did at the Old Mohawk site. And this year we had the opportunity to come in and do some post-monitoring at this site. So we looked at 3 plots that they established here in 2011, and at each plant we recorded the height, the protection status. We had 3 types of cages, as well as 2 types of ground cover, weed mats, as well as wood chip mulch. Then we also looked at the competition the plants were facing, as well as any damage they had undertaken. So our 3 main indicators of project success for this site were survival, growth, and then vigor. Generally in restoration work like this, we wanted an 80% or higher survival, and across all 3 plots, we did have an 86.4%. Just by species, you can see here that most of our deaths were from the ash, and that's from what we diagnosed as frostbite out in the field. This is a graph of the average growth of the species, the dominant species at this site, from 2011 to 2012. And it's pretty self-explanatory. The faster growing species here, the alder and the hawthorn, grew a lot more than our slower growing species, the ash and the oak. This is a vigor right here, and vigor is really one of the best indicators of project success because it shows the health of the plants as opposed to just whether they're alive or not. So to assess vigor, we looked at the average live crown ratio, which is the ratio of how much foliage there is compared to the entire tree height. So a 1 would be foliage from the tip all the way to the ground. And with our 4 deciduous trees here, what we wanted to see was anything above a 0.6. And we did see increases from last year to this year, and all well above that 0.6 range. For our 1 coniferous tree, the western red cedar here on the end, we wanted to see anything above a 0.8, which is acceptable for restoration work as successful. And even though we did see a decrease from 2011, it still is within that range. As far as damage goes, aside from the frostbite, we only really saw some minor insect damage at the site. And with our grass competition, we observed that the grass competition for the weed mats were generally within 16 centimeters, whereas the wood chip mulch limited that competition to 33 centimeters. So, conclusions for the site, we weren't really concerned with the plant damage. There's not a lot we can do about frostbite or the insects, aside from make sure that our plants are vigorous and can resist the attacks. For the ground cover protection, we did note that wood chip mulch was a lot more effective at the site for preventing grass competition, so we would recommend future management consider more of that. And as far as our 3 indicators of project success go, they all were well within the ranges of a successful project at this site. So what we really took away from this project as both a team and individuals were a lot of skills that we can really adapt to our careers down the road. We got the chance to really work on our teamwork skills. I think we have the largest team in the history of this program. So that was both a challenge and a reward in itself. We also had the opportunity to foster professional relationships with our community partners and our advisors. And my favorite part of this was the hands-on fieldwork. As opposed to sitting in the classroom all the time, we got to actually go out into the field and learn the protocols, do some monitoring, and really just go out and have some fun out in the forest. And then for all of our sites, of course, we had some data analysis compiling and management, and then we wrote up a scientific paper for each report. So we had a lot of exposure to that. Additionally, we produced a professional-looking website as a team. So that being said, we do have a lot of thanks to offer for this project. First off, we'd like to thank the Environmental Studies program here at the university for coordinating this project and making it available to undergraduate students. We'd also like to thank our two main community partners, the Mackenzie Watershed Council as well as the Mackenzie River Trust, for making the project possible. And we'd also like to thank EWEB and the Bonneville Power Administration for their participation in the BWCA project. We'd like to give special thanks to Jared Wainwright, who is our primary advisor out in the field, as well as Peg Goulet, our faculty advisor. And then additional thanks to Keith Conley, our project manager, and Pollyanna Lind, our technical advisor. And finally, we'd like to acknowledge the rest of the stream team. If you guys could stand up and take a bow. These guys were with us every step of the way, and really were just inspirational to work with us.